Hello, everyone. Welcome to the ILTA Physics online lecture. Today, we are going to learn about one of the most interesting types of motion in two-dimensional space, projectile motion. Projectile motion is a kind of movement where both the speed and the direction of the object are changing continuously. So far, we've only studied one-dimensional motion, that is, motion along a straight line, either left and right or up and down. But in projectile motion, since the direction of velocity changes, we're now dealing with motion in a two-dimensional plane. That's the key difference. Let's start by briefly introducing two main types of motion that occur in two-dimensional space. We'll also take a look at what causes an object's velocity to change direction. Then we'll dive deeper into one of these, projectile motion. Actually, projectile motion isn't a completely new concept. It's really just a combination of two types of motion we've already studied: uniform motion and accelerated motion. More specifically, you can think of two-dimensional motion as a combination of uniform motion in the horizontal direction and constant acceleration motion in the vertical direction. That means there aren't any brand new formulas to memorize. We'll simply apply what we already know in a new way. Alright, let's quickly review what we've learned so far. Up to this point, we've analyzed motion in terms of displacement, velocity, and acceleration. If we think about how these quantities are related, it's obvious that any moving object must have velocity. In other words, we could say that velocity is what causes a change in the object's position. If we focus on direction, velocity is defined as displacement divided by time interval. So displacement and velocity always point in the same direction. Acceleration, on the other hand, is defined as the change in velocity divided by time interval. So the direction of acceleration is related to the direction of velocity, but not always the same. As you can see from the formula, acceleration equals the final velocity minus the initial velocity divided by time interval. If the initial and final velocities point in different directions, then the direction of acceleration will match the direction of their difference. In other words, the vector subtraction of those two velocities. So while acceleration and velocity don't always point in the same direction, they are definitely related. That's the key idea. Now, let's look at the quantitative relationships among these motion parameters through the kinematic formulas. First, for uniform velocity motion, as the name suggests, the velocity stays constant. The object's final position equals its initial position plus displacement, as shown in the formula. Next, for constant acceleration motion, acceleration is constant. The final velocity equals the initial velocity plus the change in velocity. And the final position equals the initial position plus displacement. Although we didn't fully derive it, we know from the velocity time graph that displacement can be expressed as a quadratic function of time. If we eliminate time parameter from the equation, we get a relationship between velocity and displacement, another form of the kinematic equation. Now, if we compare the formulas for uniform motion and constant acceleration motion, they might look completely different. But actually, uniform motion is just a special case of accelerated motion, where acceleration equals zero. If we substitute I equals zero into the equations for accelerated motion, the final velocity equals the initial velocity, and the final position equals the initial position plus velocity times time interval. The third equation is also trivial. That's exactly the same as the formula for uniform motion. So we can say that uniform motion is included within uniformly accelerated motion. Pretty cool, right? Keep these formulas in mind because we'll use them again when we apply uniform and accelerated motion to two-dimensional motion. Now, let's extend our discussion to two-dimensional plane. Motion in a plane means that an object moves not just along a straight line, but over a flat surface. The direction of motion keeps changing. Look at the motion diagram on the right. The object first moves upward, then gradually changes direction to the right. So what's making the object change its direction of motion? The answer is acceleration. Then, why does acceleration change the direction of motion? Let's think about this using the formula above. Remember, all three motion parameters, displacement, velocity, and acceleration, are vectors. We're going to focus on their directions. The motion of an object in a 2D plane results in a change of position, which is displacement. Displacement is related to velocity, and they have the same direction. But according to the definition, acceleration is related to the change in velocity, not the velocity itself. That means if there is an acceleration acting in a different direction from the velocity, the final velocity will have a new direction. In summary, when an acceleration acts in a direction different from the current velocity, it changes the velocity's direction, and that change in velocity direction leads to a change in displacement direction. We'll explore this more closely using motion diagrams on the next page. From now on, we'll focus on two main types of two-dimensional motion. First, the projectile motion, which we'll study today. The circular motion, which we'll cover next time. Now let's take a closer look at how acceleration changes the direction of velocity. Think about a car turning a corner, as shown in the motion diagram. The car first moves upward and then turns to the right. If we zoom in on the section where the car changes direction, the initial velocity points roughly toward 1 o'clock. If an acceleration acts toward the southeast, the final velocity, by vector addition, will point slightly more toward 2 o'clock. So according to the rule of vector addition, the final velocity equals the initial velocity plus acceleration. Now let's think in reverse. If we know both the initial and final velocities, we can figure out the direction of acceleration. In this case, for the car to change its velocity direction from 1 o'clock to 2 o'clock, acceleration must act in the direction given by the vector subtraction of the two velocities. This is the same result as before, just viewed from a different perspective. So, to summarize, acceleration is the change in velocity per unit time. If the directions of the initial and final velocities are not the same, their difference must be calculated using vector subtraction. The magnitude of acceleration is the size of that difference divided by time, and its direction is the direction of the resulting vector. Now, let's apply this understanding to projectile motion. Projectile motion is something we can easily visualize in everyday life. For example, when you throw a ball forward, it travels through the air and then falls back to the ground. In our earlier lessons, we explained that this happens because of gravity, the gravitational acceleration of 9.8 meters per second squared acting downward. The important thing to remember is that in projectile motion, just like in free fall, we ignore any other forces, such as air resistance or engine thrust. As you can see in the figures below, there are two main types of projectile motion we'll consider. The first type is when you throw a ball horizontally from a height. The ball moves forward and downward at the same time. The second type is when you throw a ball upward at an angle. It goes up, slows down, stops for a moment, and then falls back down. In both cases, gravity acts downward, and no force acts horizontally. So how do we analyze this motion? The key idea is to separate the motion into horizontal and vertical components. The reason this works is that the horizontal and vertical motions are completely independent. They don't affect each other. All right, then let's go ahead and analyze these two types of projectile motion quantitatively. As we explained earlier, the most important idea when analyzing projectile motion is that the horizontal motion and the vertical motion are completely independent of each other. When we say the motions in each direction are independent, it means that their velocities and accelerations do not affect each other at all. Now, hold on a second. Why are the horizontal and vertical motions independent? You might not be able to give a perfect answer just yet, but we can explain it using the concept of force, which is what causes acceleration due to gravity. Force is something we'll learn more about in the next chapter. It's one of the main sources that make objects move. Gravity, in particular, acts only toward the center of the Earth, in other words, straight downward in vertical direction, and that's why it doesn't have any effect on the object's horizontal motion. Even if you don't completely understand this right now, make sure you remember this key point. Horizontal and vertical motions are independent of each other. Let's look at an example where a ball is thrown forward at an angle. The initial velocity is shown by the green arrow. We'll break that initial velocity into two parts: a horizontal component along the x-axis and a vertical component along the y-axis. Since we've split the initial velocity into horizontal and vertical components, let's now think about the motion in each direction separately. Let's first think about the acceleration in each direction and figure out what kind of motion occurs along each axis. In the horizontal direction, since there's no additional physical force acting on the object, the motion is uniform. The object moves at a constant speed. In the vertical direction, however, gravity acts downward, causing uniformly accelerated motion. In other words, free-fall motion. So, what about the velocity in each direction? The velocity along the x-axis is the blue horizontal vector, and according to trigonometric relationships, it equals the initial velocity multiplied by the cosine of the launch angle. The velocity along the y-axis is the red vertical vector, and it equals the initial velocity multiplied by the sine of the launch angle. Make sure you notice that these two velocities are simply represented as the x component and y component of the initial velocity. Now let's check the characteristics of the horizontal and vertical motions again using the motion diagram at the bottom right. The green arrows represent the direction and magnitude of the velocity at different points along the path. Each of those green velocity vectors can be broken down into a blue vector along the x-axis and a red vector along the y-axis. As you can see in the diagram, the blue vectors, which is the x-direction components, all have the same length, meaning that the horizontal motion is uniform. The red vectors, the y-direction components, gradually become shorter as the object moves upward, reach zero at the top, and then get longer again as the object falls downward. That means the vertical motion is constant acceleration motion or free fall motion. So far, we've found the horizontal and vertical components of both velocity and acceleration based on the initial velocity, and that's basically all we need. Now, we can simply plug those values into the kinematic formulas we already know and calculate the rest. Now let's organize how to solve projectile motion problems. These appear very often on exams. The first step in solving a projectile motion problem is to set up a coordinate system, just like we learned before. When we say set up a coordinate system, we mean choosing an origin and deciding which directions are positive for the motion. Usually, we take the point where the projectile is launched as the origin. Since we are going to analyze the motion separately along the x-axis and y-axis, we'll set the positive x direction to the right and the positive y direction upward as the positive directions for this projectile motion, just like in a standard coordinate system. Next, in the second step, we'll use the initial velocity and some basic trigonometry to find the velocity components along the x and y directions. If you imagine the diagram shown in the bottom right corner, you really don't need to memorize any formulas. It's all about visualizing how the velocity splits into two perpendicular components. Once we know the velocities in both directions, we can start by analyzing the horizontal motion. Because the horizontal motion is uniform, the acceleration is zero, which means the initial velocity and the final velocity are the same. In uniform motion, the final position equals the initial position plus the horizontal velocity multiplied by time interval. Next, let's look at the vertical motion. This is uniformly accelerated motion or free fall motion. Since we already know the initial velocity in the vertical direction, we can use the kinematic formulas for accelerated motion to find the final velocity or the final position. These are the constant acceleration motion formulas we learned earlier, with the initial vertical velocity and gravitational acceleration plugged in. Finally, if the problem asks for the total velocity at a certain position, we can use the final velocities in the x and y directions that we just calculated. Using those two perpendicular components, we can find both the magnitude and the direction of the final velocity. This relationship comes from the vector addition of two perpendicular vectors, which shows the magnitude of the resultant vector and the angle it makes with the positive x-axis. Finally, let's summarize some useful tips that can be very helpful when solving test problems involving projectile motion. First, the time a projectile spends in the air is determined entirely by the motion along the y-axis, which is uniformly accelerated motion, specifically freefall motion. This is because the motion in the horizontal, or x direction, is constant velocity motion. Since there is no acceleration in the horizontal direction, the object's speed theoretically cannot change and thus, it cannot come to a stop. Therefore, the duration it takes for the object to fall back to the ground due to gravity is precisely the object's time of flight. Second, when a problem mentions the expression when the object reaches its maximum height, you should solve the problem by setting the velocity in the y-axis direction to 0. In other words, a rising object momentarily stops when its velocity becomes 0. Logically, in the motion where an object flies upward, momentarily stops, and then falls back down, this point of instantaneous rest is the moment it reaches its maximum height. Okay, let's review the approach to projectile motion problems using the diagram below. Use the initial velocity to find the initial velocities in the horizontal x direction and the vertical y direction separately. Using these initial velocities, apply the uniform velocity motion formulas for the horizontal direction and the uniformly accelerated motion formulas for the vertical direction. As explained in the tips above, the time of flight is calculated based on the vertical free fall motion, and finding the maximum height is done by setting the vertical velocity to 0. Please practice by solving many problems using this method. That concludes today's lecture. Thank you all for your hard work.